So, once you have now defined a derivative, the game is now to know how to play with it. Many of you who have already done calculus in high school, I am sure knows how to play with it. So, in order to play with it, some rules have to be formulated. So, this is what are called rules of differentiation. It tells you if I combine two functions in different ways, then how am I going to find the derivative of that combined function. So, how many ways you can combine two functions? First of course is if I add the two functions f and g, and then second if I subtract the two functions f and g, then of course comes multiplication, and then comes division, where of course I need to know that g cannot be 0. So, if I know that the function f and the function g has a derivative, how do I compute the derivative of f and g? So, derivative is sometimes also written like this. Or if you write y is equal to fx, some people also prefer to write this. It depends on what is your choice. It's no hard and fast rule, you can invent your own if you want. Now, so what is the, how do I compute the derivative of this function? Knowing the fact that limit of f plus g is limit of f plus limit of g, just so if you write down the derivative, definition of the derivative of this and separate them out, you can easily prove that proving this is not a very difficult situation. For example, another thing I just wanted to, I didn't give you is, if I have f of, so I multiply c with x where c is constant, then how would I calculate the derivative? Now, in this case you know what is the meaning of f minus g, that is at any point x the functional value f minus g is evaluated as fx minus gx. So, if I compute the derivative of this would give me just give me this. So, this is pretty well known. A slightly complicated one is this product, and you know that if the product function f g when evaluated at x is nothing but f of x into g of x, and so when I am trying to find the derivative of this function, then I have we have to make a little more manipulation, and I think this is a good exercise for anyone to try at home who wants to sharpen his confidence in handling things in calculus. So, this is gx into f dash x plus fx into g dash x. So, here is an interesting looking formula. This is essentially nothing but manipulation of that limit. So, how do you manipulate the limit and what you do? So, this is exactly what you will get. I would very strongly suggest that those of you who are watching the program, take a pen and pad, you can stop the program for some time, work it out and see whether I come to this conclusion or not. This is a slightly tricky one. Of course, gx cannot be 0 for any x. So, when I want to evaluate this is a slightly tricky one, but again it is the same thing what you do with, because this is nothing but f multiplied with 1 by g, where g is a non-negative function. So, this is what you have. So, these are suggested things that you need. I would suggest that this is slightly more complicated than these two. So, you have to do some manipulation. So, kindly check out. This is very simple, of course. This says that if you have this function, that is you multiply C with x and operate f. Of course, you can ask what is the domain and range of f and g, all these things can be asked. You can take the domain, or domain could be say the interval a b to r, and g could be also interval a b to r, or interval open interval c d to r, where a b and c d has some intersection, or you can just say both of them are from r to r, does not matter. So, this domain and range does not matter if the function is differentiable at a given x, and then that is exactly. So, essentially this is a point based result, that we are talking about the differentiability at this particular point. So, that is how you will calculate the derivative for this. So, if I know the derivative of this and this at this point x, then I know the derivative of f plus g at the point x, and so on and so for the rest of the writings. So, so if I want to find the derivative of this is nothing but sorry, it should be C of f. So, C of f means basically C of f at x is nothing but C of f x. So, when you take this function and try to find the derivative at x, this gives you C of f dash x. That is a constant comes out of the differentiation. So, these are standard one. So, you see we have covered almost all the known operations, but there is another important operation, and this is important, and this is one of the key rules that you need to bother about. Here we are talking about two functions f and g, and we are talking about the composition of the two functions, and we want to compute the derivative of this composition. How do we do this? Many of you would immediately jump and say, oh, this is the chain rule. Yes, this is a chain rule, but the ease with which you will prove this, with the same ease you will not be proving this thing, and you need to be slightly careful when you talk about this problem. So, if you want to compute say the derivative at x, or say at a point a, then what you do is you compute the derivative of f dash at gx, and then you compute g dash x. So, how does this formula arrive? You can say, oh, I can just do the same, I can just write down the limit, and I can do something, and I can, for example, I can do this. So, I am computing it at some a, say. So, basically I should have right. So, of course, we are all talking about differentiable functions, but please do not ask questions in the forum which are very obvious. When you are talking about rules of differentiation, I have to really focus only on differentiable functions. I cannot be talking on functions which are not differentiable. So, that is the definition of the derivative. So, you think, okay, I have to get something like this. So, somehow I have to bring that g dash x in. This is a formula somebody tells you, and you decide that, okay, I really have to bring in this, and that would be enough, right. So, what do you intend to do? Now, how you will progress to get this g dash x. So, let us see that. So, you think okay, somehow I have to get this g of a plus h minus g of h, that sort of thing should come in. So, I can write this as, and that is exactly what you will be taught in most places. I will do some manipulations. Here I will add a GA and subtract a GA. What I do now, I multiply both top and below by so you say, oh, that is done, because of course for the definition of composition f must be defined on the range of G, and hence by Jove this is acting as my H, GA plus H minus GA is acting as my H or K basically, the increment. So, then this term basically tells you, so what I did was I divided and multiplied by GA plus H minus GA. So, this term simply tells you that okay fine. So, this will be, so now I operate the limit here, limit of f into fg is limit f into lim g if both the limit exists. So, now what I will simply do is take the limit of this and then the limit of this, and this will simply give me f of f dash of g a, and that would give me g dash of a. You say, voila, I have done it. But I would ask you to, as I explain some goodies which the chain rule gives us, I would ask you to think whether this proof is correct or not, whether this proof is mathematically rigorous or not. And that is why, and you once you can figure out what I am trying to say, you will really start appreciating the nature of mathematical proof and why we really need in mathematics to demonstrate things rigorously. See, one thing which I have seen students often do, it does not matter where are you the student. See, it is usually assumed okay dy dx is 1 by dx dy, as if it is just like a fraction. Right. But it is not a fraction essentially, but this is an operator, it is a. So, how do I, so it simply means that dy dx into dx dy is equal to 1. So, how do I justify this? This justification actually comes from the chain rule. This justification actually comes from the chain rule, because the function y, if I take this is 1, right. So, once I can write x also as a function of y, that is x, this function or rather y is a function of x, that you of course know, but if you write if you can write x also as a function of y, means the function is invertible, only for that case you can definitely write, you can talk about this term dx dy. You know y is a function of x, and if it is invertible then x can be represented as a function of y, and then in that case you can write this thing as that composition of a function y is a composition of the function into its inverse. If you compose a function with its inverse, if the inverse exists, it gives you back the function. So, then what happens is this can be written as first and then x as a function of y, and this is its standard that is 1. So, this is what happens. So, it is a chain rule which is the key fact which proves such things, and of course, it is not, you just do not write things like this, it is not always true. It is only true when your function is invertible, you can actually apply the chain rule, right. So, you have to be very careful that I should be able to express x as a function of y, then only you can do dx dy, right. You cannot just write something like this from the air, okay. But most of the things in calculus that we do are essentially of that nicer form, and so you can do things, but not always, every function does not really have an inverse. So, now where do you think is the problem with this proof? The problem with the proof lies in the fact that no one told me that GA plus H minus GA is not equal to 0. If I move a little bit from GA, the function could be would remain constant over a little zone, or maybe it is just constant after some time, and G of A plus G of A plus H could be just 0. How do you accommodate that situation? There is no way I can tell anything if that happens here, and that tells us that this approach of actually proving the chain rule, which is quite standard in many ordinary calculus texts, is actually wrong. So, you really have to know the correct steps of proving this rule, and that is exactly what we are going to now do. So, our discussion today would end with the true proof of this chain rule formula. And this proof I am doing from the book of Spivak, as I told you that I suggest that this book be actually kept in the library of every good school, and students should have an access to it. This is a school or high school or even college or whatever, does not matter. That this book, now at least in the colleges in India, so that kids could have a better access to proper knowledge basically. So, here is the chain rule, and I write down the theorem. Let f be differentiable at GA and G be differentiable at A. So, I will write the author whose proof I am now using, whose proof style rather. Because quite a part of this course I will follow this book, but I will also show you some more interesting books which you can read. G be differentiable at A, then f compose G is also differentiable at A, see, we are not bothered much about the domain and range and of f and g, this is obvious. This is just, you can do it over any open interval or the whole R, does not matter. And this is what you will have. That is exactly the same thing that I am going to repeat here. So, f dash evaluated at GA into G dash A. Now, how do I start doing the proof of this? Okay. The proof begins by constructing a function called phi h, which has similar structure like this, right, because you see this thing is nothing but g of a plus h minus f g a by this. So, I will construct phi h which is of this form, that is f of if and it is f dash of g a if so, that is how I have defined this function. The next step that we will use is trying to prove the continuity of the function phi. So, the function phi you can easily prove that it is continuous at the point 0 when h goes to 0, because that is what we have to check at the function, this function phi is continuous at 0, right. So, that you can figure out, because if h goes to 0 it does not matter if h, and this is not equal to 0, and if h goes to 0 this is nothing but f dash g of a, and if this is 0 it does not matter if h goes to 0, and if this continues to remain 0 then also the limit is nothing but f dash g of a. So, this is nothing but f of that is nothing but phi of 0. So, whenever h is 0 this is 0. So, you will always have this. So, phi is continuous at 0. So, now let us do it step by step, and you will see how the whole thing evolves, and that will be very nice and beautiful. Working with the chain rules is something which you can easily figure out in any calculus book. My idea here again, as I told you in this course, is not really to show you doing examples and examples, it is to give you the conceptual issues in calculus. When how do you really think about a problem, how do you really think in calculus. So, that is the key idea. So, now so whatever we have just said that phi is continuous at 0, that was just a idea, brief idea that we have given, but we will just prove that phi is actually continuous at 0, and that we will do very step by step. So, f is differentiable at G A or whatever, f is differentiable at G A. So, what does that mean f is differentiable at G A? It means the following, that f dash of G A is equal to limit k tends to 0 f of G A plus k minus f of G A by k. So, given epsilon greater than 0, so given epsilon greater than 0, there exists say delta dash greater than 0 such that for all k with what would I have? I would have f of GA plus K minus f of GA. You see, this is a rigorous argument. Here there would be no flaws in the logic. I am not going to get into the foundation and all these aspects of mathematics, but there is no flaw in the logic as a standard mathematical logic goes, there is no flaw in our logic. So, this demonstration is absolutely all right. You know, mathematics has evolved over the ages, and I want to tell you what was a very logical thing in the early part of the 20th century or late part of the 19th century is not possibly could be considered logical. Many of proof of great mathematicians like Euler's, whose results are all correct and the proofs are completely wrong by our current standards. So, the whole notion of proof evolves as the subject evolves itself. So, here, so till now what we are doing at this point of our evolution of mathematics, what we are now doing is accepted to be rigorous. So, everything there is a little pinch of salt, but that is all right. So, minus f dash of GA, this must be less than epsilon. So, this is a standard definition, you already know. I have already spoken about the derivative and given this definition. So, this is what you already know. Okay. Now, G is differentiable at A, right. So, which implies that G must be continuous at A, okay, because every differentiable function is continuous, something which I told that all of you try at home, those who are observing this, those who are looking at this video should try that at home, because without trying stuff you will not be getting anywhere, and that is the most important thing. So, G is differentiable at A, this is the crux. This argument that here you are using an important fact that whenever G is differentiable at A, G is continuous A, this is the crux of this whole proof, that phi is continuous at 0. If you want to make it rigorous, this is the crux of the proof. If you just use a differentiability definition of G, you would not get anywhere, that is the crux. So, implies G is continuous at A. So, if I now for G I consider this delta dash to be my epsilon. So, corresponding to delta dash, corresponding to that delta dash, corresponding hence corresponding to delta dash greater than 0, there exists delta greater than 0 such that for all H with mod H strictly less than delta, it implies that G of A plus H minus G of A is strictly less than delta dash. Now, this result, this fact given epsilon there exists delta dash for which this holds is true for any K which satisfies this. Okay. Now, assume that G of A plus H, now assume let G of A plus H minus GA is not equal to 0.
Sorry, there can be equality there, 0 less than equals to mod K, because here also again the same thing can happen, that G of A plus
No, this is a definition of the limit. You see, this is the definition of the limit. Limit you would always take a punctured neighborhood. You are writing the definition of the limit. The functional value at when K tends to 0 is not this. Of this differential quotient, this is not the functional value. Because K tends to 0, this has at K equal to 0, this has no definition. It is undefined at K equal to 0. This differential quotient. So that cannot be continuous. So this is correct. This is a standard definition of the limit. So here I have using the continuity. So because it has to be defined at H actually at A. So here H can be 0 because as you know it has to be defined at A. Now suppose this is not equal to 0, but I have shown that for all mod H less than delta, this is less than delta dash. Now set G of a plus h minus GA to be k. Now, for all mod h, so now for mod h less than delta, so what happens? It implies that mod k, which is bigger than 0 now, because this is not 0, is less than delta dash because of this statement, because now I assume that g of a plus h minus g of k. So, it satisfies it. So, g of a plus h minus g of a is one of these k's. So, which implies that if I replace that k, so f of g a plus k, that is, so if I write here k as g of a plus minus h minus g a, so I will simply have here g of a plus h minus f of g a. So, I am doing this part of the proof here, delta dash. So, we will have this divided by, instead of k, I will now have g of a plus h minus g a minus f dash g a strictly less than epsilon. So, for all mod h less than delta, this is this. So, what is this? This is nothing but, that is nothing but phi h minus, because whenever g a of a plus h minus g a is not equal to 0, phi h is defined like this, that is phi h, f dash of g a is strictly less than epsilon whenever mod h is less than delta. So, this is true when, so which means whenever h is tending to 0, and this is also can be made smaller and smaller. Now, if this is equal to 0, g of a plus h minus g a is equal to 0, I have already defined f of phi of h as f dash of g a. So, their difference would be anyway 0 and would be less than any epsilon that you choose, because epsilon is positive. So, it means that for mod h, when for mod h less than delta, phi h minus f dash of g a is strictly less than epsilon, right, it doesn't matter. So, this is true. So, what I have proved that limit phi of h as h tends to 0 is f dash of g a. This is the crucial step by which you overcome the fact that g of a plus h minus g a could be 0. So, now I will finish this part, the rest of the proof, which is not difficult. I am just removing this part. And we will finish this rest of the part, and hence our discussion on rules for differentiation. This is the most important rule, one of the most important rules of calculus, and where many people actually do not understand it very clearly how to handle it. So now what I can write? So, now let me write f of g a plus h minus f of g a by h. This thing can be written as phi h into, means this thing, into g of a plus h minus g of a by h. Right. So, because this is nothing but, so what I have now written, I have written f of g of a plus h minus f of g of a divided by h is equal to phi h into g of a plus h minus g a by h. Now, here if it is g of a plus h minus g h 0 does not matter, because if g of a plus h is equal to g a, then this is 0 and then this is 0 0 0 both sides, so it does not matter, it holds. Now, you see why this phi h tending to 0 was crucial. Now, if I apply the limit as h tends to 0, I will apply it on both the sides, limit as h tends to 0. So, this is nothing, what is by definition? By definition is this. Now, because the limit of these two quantities exist, so the limit of this side also must exist, and hence f compose g is differentiable at a, and this is nothing but limit of h tends to 0 phi of h into limit of h tends to 0 g of a plus h minus g a by h, and you have already proved that limit of phi h is equal to 0. And see, this is the beauty of mathematics, that everything can be proved in a very rigorous fashion. So, this is, you already know that this is nothing but f dash of g of a, and you see the power of the epsilon delta reasoning, just because of this proof is rigorously done because of the power of that reasoning, and this is nothing but g dash a, and voila, we have proved this. So, we have proved this game. So, with this we end this discussion. I hope you enjoyed this proof, because I think it is a very nice, very beautifully done thing. And after this we will talk about one of the things which is very close to my heart, about maxima and minima, and which is a very important application of this side, this notion of derivative, which we will start in our next lecture. Thank you very much.